This video is an introduction to triple integrals and cylindrical coordinates found in section 15.7 of our text. Okay, so cylindrical coordinates are polar coordinates in 3 dimensions. So a point in cylindrical coordinates is an ordered triple r theta z, where r theta is the same r theta we have in polar coordinates if we were to project the point P onto the xy plane. So if we were to take the point P and push it down into the xy plane, then r would represent the distance from that point, that projected point, to the origin, and theta would represent the angle between the positive x-axis and the line segment from the origin to that projected point. And z still represents directed distance from the xy plane to the point P. And here actually is another really nice image for our cylindrical points and kind of gives you some understanding maybe as to where they get their name. So again, the r theta is the projection of the point P into the xy plane, and then z just gives us the directed distance from the xy plane up or down to the point P. Now, because the r and theta are the same r theta that we have from our polar coordinates, then we have the same relationships. X is still our cosine theta, y is still our sine theta, the tangent of theta is still y over x, and x squared plus y squared equals z squared. So these same relationships still hold in cylindrical coordinates just like they do in polar coordinates. And because z is still directed distance from the xy plane like it usually is, then z just gets to stay z. So that's really nice. And here's an example of a cylindrical point 2 pi over 3, 1, just to give you an idea. Okay, so suppose we want to convert the point with cylindrical coordinates 2 pi over 4, 1 to rectangular coordinates. So we've been given the cylindrical point where r is 2, theta is pi over 4, and z equals 1. And we want to rewrite this as an x, y, z. So we first recall that x is our cosine theta. And so in this example, we'll have 2 cosine of pi over 4, which simplifies to the square root of 2. Similarly, y is our sine theta. So in this example, 2 times the sine of pi over 4, which is the square root of 2 as well. And then since z gets to stay the same, z remains 1. So this point in rectangular coordinates would be the point xyz equals square root of 2, square root of 2, 1. Okay, so going from cylindrical coordinates to rectangular coordinates is really straightforward. Now let's do one where we go backwards, and we'll say those are a little bit more complicated, and the complication comes because polar coordinates are a little more complicated because the way that you represent a point is not unique, and you'll see what I mean. Okay, so in this example, we have the rectangular point xyz equals 1, negative 1, 4, and we want to rewrite this as an r theta z. So first, recall that r squared is x squared plus y squared. So in this example, we have 1 squared plus negative 1 squared, which is 2. And therefore, r is positive or negative square root of 2. Now, we're going to have to make a choice whether we want the positive square root or the negative square root, but we don't yet have enough information to make that choice. It relies on our choice for theta as well. So we've got to pause on the r for a second. We'll come back to it shortly. So next up is the theta. We know that tangent of theta is y over x, which in this example will be -1 over +1. So tangent of theta is -1. And we usually want to choose a theta between -π/2 and +π/2. And that's because this is the range of theta for which the arctangent is defined. And so if we want to restrict ourselves to those values of theta, then we would choose theta to be -π/4. That's the value of theta where tangent is -1. Okay, so now we're ready to make our choice for r. And we've got to remember that the point that we're interested in, the xy point that we're recreating here, is the point 1, -1. And you see it plotted here, and it's in our fourth quadrant, of course. And we've made the choice for theta to be -π/4. And so if theta is -π/4 and we're wanting to get the point 1, -1, then that tells us that we should choose r to be the positive square root of 2. Great, so we've made our choice for r and for theta. Because z gets to stay z will stay 4. And so our answer would be that r is the square root of 2, theta is -π/4, and z is 4. Okay, now if that idea of having to make that choice for r was a little bit confusing, let me see if I can help it make more sense by changing the example slightly. So instead of 1, -1, 4, I'm going to make a change. And let's instead consider the point -1, +1, 4. So that's our x, y, z this time. Our computation for r goes exactly the same way. R squared is still 2. So r will still be positive or negative square root of 2. Tangent of theta is still -1. And so if we want to make a choice for theta between -π/2 and +π/2, then we would still choose theta to be -π/4. Okay, here's where the change comes in. Notice that in this example, our xy point is -1, +1, which is in the second quadrant. But we still have a theta of -π/4. So if we choose +2, excuse me, that should be a positive square root of 2, -π/4, then that would put us at the green point that we see here. And we don't want the green point, we want the red point, right? So the only way to shoot ourselves into that second quadrant is to choose r to be the negative square root of 2. Hopefully that makes a little bit more sense. And the z remains 4. So our cylindrical point here would be negative square root of 2, -π/4, 4. Okay, but that's enough about points. Let's talk about integrals, right? So suppose we want to compute a triple integral over a region E, where in the region E, z is bounded between two functions, u1 and u2. And if we project E into the xy plane, we get a region D, where in the region D, we have a polar wedge where theta is bounded between alpha and beta, and r is bounded between h1 and h2. So that projection into the xy plane is best described using polar coordinates, r's and thetas. So in that case, our triple integral will look like this. So our theta bounds will go from alpha to beta, our r bounds will go from h1 to h2, our z bounds will go from u1 to u2. Anywhere we see an x, we'll replace it with r cosine theta. Anywhere we see a y, we'll replace it with r sine theta. Anywhere we see a z, we'll keep it as z. And then you can think, because of this carryover from polar coordinates, we will have an r dz, dr, d theta. So just like we do with our double integrals in polar coordinates, we will have this extra r that becomes a part of our integral that we don't want to forget. And another way to remember and visualize where that r is coming from, if we think about the volume element in cylindrical coordinates, to the volume of a box, right, we think of as being our height times our length times our width. And so our height here would be that dz, our length would be dr, and then the width is actually an r d theta. And so that's where that r is coming from. You can think about it that way as well. All right, let's do an example. Let's evaluate the triple integral over e of x cubed plus xy squared, where e is the solid in the first octant that lies beneath the paraboloid z equals 1 minus x squared minus y squared. Okay, so we're going to start with sketches of both our region E, the three-dimensional surface E, and its projection D in the xy plane. So for E, we have the paraboloid z equals 1 minus x squared minus y squared, and we'll want to rewrite that in cylindrical coordinates as 1 minus r squared. And to help us visualize that, we've got a paraboloid as we're told, right? So one of these like three-dimensional parabolas that's been turned upside down and moved up 1 on the z-axis. Okay, now for D, the projection in the xy plane. So in the xy plane, z of course is 0. And if we let z equal 0, then our equation of our paraboloid becomes x squared plus y squared equals 1. So we're talking about a circle centered at the origin of radius 1. And we're asked to only consider the first octant, so we only want the piece of that circle where x and y are both positive. So we can describe then our surface E as the cylindrical points r theta z's, where r lives between 0 and 1, and theta lives between 0 and pi over 2, and then where z lives between 0 and 1 minus r squared. Okay, so let's go to a clean slide to give me a little bit of room here. And before we integrate, we've got one other piece of business. So the function that we are integrating, x cubed plus xy squared, we want to rewrite that in cylindrical coordinates. So we can factor out the x, and the x, of course, becomes r cosine theta. And then the x squared plus y squared is equal to r squared. So when we put that together, we have an r cubed times the cosine of theta. Okay, so our triple integral over E looks like this. Our theta bounds go from 0 to pi over 2. Our r bounds go from 0 to 1. Z goes from 0 to 1 minus r squared. The function that we're integrating simplifies to r cubed cosine of theta. And then because we are doing a cylindrical integral, we'll always have to include that extra r in front of our dz, dr, d theta. Great. So we integrate first with respect to z, and I'm actually going to do two steps at one time. My apologies. I'm going to combine the r cubed and the r to give us an r to the fourth, so that's where the r to the fourth comes from. And then everything there is a constant as far as z is concerned. So when we integrate with respect to z, we get an r to the fourth cosine of theta times z, which we'll evaluate for z from 0 to 1 minus r squared. And so when we do that, we get the double integral of r to the fourth times cosine of theta times 1 minus r squared. All right, new slide because I'm out of room. There we are. So I'm going to multiply the r's together. So I'll have an r to the fourth minus r to the sixth times cosine of theta. We integrate with respect to r. That'll give us a 1/5 r to the fifth minus 1/7 r to the seventh times cosine of theta. We're going to evaluate r from 0 to 1, and that will give us a constant of 2 over 35. So we get 2 over 35 times the integral from 0 to pi over 2 of cosine of theta. And so that is 2/35 times the sine of theta, evaluated from 0 to pi over 2. So our final answer is 2/35. Great, so that's all for this introduction, and we will work more with cylindrical coordinates together in class. Thanks, guys. Bye.